In this lesson, you'll learn how to graph a polynomial function and locate the real zeros, and find maxima and minima of polynomial functions. How can graphs of polynomial functions show trends in data? The percent of the United States population that was freeborn since 1900 can be modeled by P of t equals 0.6 t cubed minus 7,000 t squared plus 500 t plus 14, where t equals 0 in 1900. Notice that the graph is decreasing from t equals 5 until t equals 75. At the points t equals 5 and t equals 75, there are turning points in the graph. To graph a polynomial function, make a table of values to find several points and then connect them to make a smooth curve. Knowing the end behavior of the graph will assist you in completing the sketch of the graph. This isn't too bad given our calculators with a table feature. So they want us to graph it making a table of values. So if we substitute -4 for x, we'll get out a value of 5, -3 is -4, -2, -3, -1 is 2, 0 is of course 0 plus 0 plus 5 is 5, 1 is 0, and 2 is -19. And they plotted the points and connected them with a nice smooth curve. You can see that they knew somehow that there was a minimum below that point. This must have been the absolute maximum, and we don't have an absolute minimum because it keeps going down. This is an odd degree polynomial with a negative leading coefficient, so that f of x approaches positive infinity as x approaches negative infinity, and f of x approaches negative infinity as x approaches positive infinity. Notice that the graph intersects the x-axis 3 times, indicating there are 3 real zeros. To graph polynomial functions, it will often be necessary to include x values that are not integers if we wanted to get that minimum. In example 1, zeros that occur at integral values can be seen in the table and used to plot the function. Notice the values of the function before and after each zero are in a different sign. So in our table we had positive 5 and -4, so somewhere between positive 5 and -4 there's a 0, and -3 and positive 2. Again, somewhere between -3 and positive 2 is the number 0. In general, the graph of a polynomial function will cross the x-axis somewhere between the pairs of x values at which the corresponding f of x values change signs. Since zeros of the function are located at x-intercepts, there is a 0 between each pair of these x values. This property for locating zeros is called the location principle. Suppose y equals f of x represents a polynomial function and a and b are 2 numbers such that f of a is less than 0 and f of b is greater than 0. Then the function has at least one real 0 between a and b. Determine consecutive values of x between which each real 0 of the function f of x equals x to the 4th minus x cubed minus 4x squared plus 1 is located, then draw the graph. Once again, you're very blessed to have inexpensive calculators with a table feature. So we can type that in our table feature, and if x is -2, f of x is 9, and -1, I get -1, 0 gives me 1, 1, -3, 2, -7, and 3, 19. I can see I went from positive to negative, and back again, negative to positive, and again, positive to negative. So there are my 3 and 4 zeros. And they've plotted the points, and notice again, they kind of cheated a little bit with the aid of technology because they knew there was a minimum that was less than the one they got from the integer. And we'll also run into this problem. 9 we could have used graph paper and got to, but 19 is going to be way up there. So sometimes our graph paper is just going to have to shoot for the sky, hoping to get to where it should be. So from our sign changes and from the graph, we can see there are zeros between x equals -2 and -1, -1 and 0, 0 and 1, and 2 and 3. I like this notation as opposed to writing out the words. It looks more concise. The graph at the right shows the shape of a general third-degree polynomial function. Point A on the graph is a relative maximum of the cubic function since no other nearby points have a greater coordinate. Likewise, point B is a relative minimum since no other nearby points have a lesser y-coordinate. These points are often referred to as turning points. The graph of a polynomial function of degree n has at most n minus 1 turning points. So in this graph we have a third degree equation and there are 2 turning points. Graph and estimate the x-coordinates at which the relative maximum and minimum occur. So using the table feature, we've got -2, -19. Again, my graph paper is not going to be that big. -1, 0. 0 is, of course, 5. 1, 2. 2, -3. 3, -4. 4, 5. And 5 is clear up to 30. So for -2, we're not quite to -2, and we're going clear down because we know we can't get to -19. The same thing over here. I'm not going to get quite to 5, and I'm shooting towards 30. I have a third degree equation, so I should have 2 turning points. It looks like we have a relative maximum when x is 0, f of x is 5, and a relative minimum when x is 3, f of x is -4. Now they did say estimate, and you can see on their graph it in fact did go a little bit lower. If we used GeoGebra, we could get the exact minimum. The weight W in pounds of a patient during a 7-week illness is modeled by the cubic equation given, where n is the number of weeks since the patient became ill. These were large numbers, so I didn't make you wait for me to calculate them using the calculator. I just gave you the table. And you can see on the graph they admitted that they did the 1, 2, skip a few, and they have a little interruption here, which is fine because they admitted it. And they plotted the points, and their weight is going back up. Describe the turning points of the graph and its in behavior. Well, I can see one nice turning point. There's a relative minimum at week 4. For the in behavior, W of n increases as n increases. What trends in the patient's weight does the graph suggest? The patient lost weight for each of the 4 weeks after becoming ill. After 4 weeks, the patient started to gain weight and continues to gain weight. The graph of a polynomial function will cross the x-axis somewhere between pairs of x values at which the corresponding f of x values change signs. Since zeros of the function are located at x-intercepts, there is a 0 between each pair of these x values. Turning points of a function are called relative maxima and relative minima.